Hello, friends. Hi, everybody. I just wanted to say thank you all for your interest in our continuing science diplomacy, and in particular space diplomacy lecture series here at the Duke Center for Global and International Studies, Rethinking Diplomacy program. My name is Benjamin Schmitt. I'm a postdoctoral research fellow here at the Harvard-Smithsonian Center for Astrophysics, coming to you live from Cambridge, Massachusetts. And we're here today to talk about a real diplomatic, national security, technical, and science issue, really cross-cutting and multidisciplinary, as we like these issues to be here in this series. And we're talking about space debris. So for the past 2 weeks, we've seen policymakers pause to look up and address climate issues that are churning within our own atmosphere at the COP26 summit in Glasgow. With the same spirit of science diplomacy, those leaders should also tilt their heads back a bit further to address another predicament rapidly unfolding above our heads: the proliferation of space debris, sometimes referred to as space junk, debris in low Earth orbit and beyond. Imagine a future in which both human and satellite spacecraft are increasingly vulnerable to catastrophic collisions with debris, ranging in scale from spent rocket components as large as a city bus to defunct satellites, and on down to nuts, bolts, and even smaller debris the scale of paint flecks. This really matters if humanity is to reap the economic and strategic benefits that are newly accessible in the space boom of the 2020s. If left unaddressed, the consequences of an unmitigated space debris field growing around Earth's orbital domains could doom humanity's burgeoning space future before it truly begins. So here to talk about this today, I'm joined by our special guest, Dr. Hugh Lewis. Dr. Hugh Lewis is a professor of astronautics and the head of the Astronautics Research Group at the University of Southampton. He's worked in the fields of space debris and space sustainability for more than 20 years and is the author of the Damaged Space Debris Model. Hugh represents the UK Space Agency at meetings of the Interagency Space Debris Coordination Committee, where he chairs Working Group 2, which is focused on space debris modeling. He was also represented in the UK Space Agency and Scientific and Technical Subcommittee meetings of the United Nations Committee on the Peaceful Use of Outer Space as an expert on space debris, space operations, and space situational awareness. In addition, he was a UK Space Agency delegate to the Space Mission Planning Advisory Group, which was set up by the UN to develop plans for spacecraft to monitor and mitigate the threat that asteroids and comets pose to Earth. He provides expert opinion to space industry and academic committees and commentary to journalists worldwide. He's also appearing in our program here today. And Hugh has also appeared on the BBC Horizons television program and in a special feature accompanying the DVD and Blu-ray release of the movie Gravity. Here also on the panel to discuss the space debris issues and to facilitate more questions and answers, I'm joined by Ambassador Bob Pearson, also of the Duke Rethinking Diplomacy program, Professor Britt Lundgren, an Associate Professor of Physics and Astronomy at UNC Asheville, and Professor Laura Newberg, Assistant Professor of Physics at Yale University. So with this, I'm going to turn this over to Dr. Lewis, but not before taking just a moment to allow everyone to visualize this space debris scale and problem by showing you the live plot that you can see right now in a website called stuffin.space, which draws data directly from the US Space Command's spacetrack.org program. So what you're seeing here is basically everything that's above 10 centimeters in diameter or so that is orbiting the Earth in some capacity. The gray dots are space debris, the blue dots are rocket components, and the red dots are satellites. If it doesn't give you the scale of what we're talking about today, I don't know what will. This is a great visualization that I've spent hours looking at already, and I encourage all of you to go there after the event. So I will stop sharing and hand this over to Dr. Lewis.
Many thanks, Ben. Really appreciate the invitation to talk here and to have what is, I'm sure, going to be a really fascinating conversation. So I'm going to start by giving you a short presentation which is focused on ideas. So this is not going to be a presentation that includes graphs or charts or even, in fact, many words. It's all about ideas. And you can probably tell, being born in the 1970s, growing up in the 80s and 90s, some of the images are going to come from movies from that time. Some may be a bit more recent as well. And these images represent the ideas that I'm going to try and share with you. And it's really a presentation that is going to pose some questions, identify some problems, and then hopefully lead us towards the conversation about what the solutions might be. So as Ben has already quite well explained and shown you, that there is a lot of debris around the Earth. So this is probably the only time that I'm going to tell you about some statistics associated with the space debris problem. The European Space Agency estimate there to be about 36,500 objects that are in orbit that are larger than 10 centimeters, about 1 million objects that are larger than 1 centimeter, and then actually 1/3 of a billion objects that are the size of a millimeter or larger. So the population obviously is extremely extensive, and it poses a very substantial risk to space systems that we have come to rely upon here down on the Earth. Systems that allow us to understand the planet, systems that allow us to communicate, systems that allow us to be entertained through television and so on. And without those services, we would obviously, all of us, the entire planet would suffer. And it's very important that we are able to protect the satellites that provide those services from all the threats that exist. And space debris is one of those. The orbital speeds that we're talking about are very important to acknowledge. So typically in low Earth orbit, that's the region between about 200 kilometers and 2,000 kilometers, the speeds are anywhere upwards from about 7.5 kilometers per second, maybe up to 10 kilometers per second, depending upon the orbit. So the relative speeds can be absolutely huge. And even a very small object, therefore, poses a very substantial risk to the satellites that I've been talking about. What's interesting about space debris problem is that it's a wicked problem, which is not a word I'm making up, by the way. There's a class of problems, and in fact, the space debris problem is what we'd refer to as a super wicked problem. And one of the key problems that exists, one of the key challenges of this type of problem is that the problem is distant, not just in time, but also in space. So for us down here on the Earth, we are really not aware of the problem, this growing problem that exists in orbit. And it's very difficult for us to make a connection to it as a result. So what we see for things like climate change and the impacts of climate change is actually, unless we make that human connection, it's not something that we would tend to address. And we're seeing this, we've seen in the last couple of weeks with the COP26 meeting here in the UK, that actually there's a lot of things that we do need to discuss, and we do need to start to understand from our own individual perspective. And here's example, Tuvalu's Minister of Justice, Communication and Foreign Affairs, giving a press conference from a site that has been overtaken by the sea as a result of climate change. So there's a really great connection between us as a population on the planet and a particular problem. It's actually very difficult for us to do the same thing for the space debris problem. But we do have, I guess, a bit of an advantage, which is our imaginations. And something that I think was very successfully done back in 2013 was to put or to give us the opportunity to experience the space debris problem from the perspective of an astronaut. So in this case, the astronaut played by Sandra Bullock in the movie Gravity. So setting aside perhaps all of the technical, scientific issues that you might have had with that particular movie, one of the best things about that movie is it put a human being into the environment that is at risk, and it's the environment that we're talking about. And that gave us the opportunity to understand the scale and the nature of the problem. So in many senses, we have to rely on our imagination. So I'm going to be urging you throughout the rest of this short presentation just to continue doing that. Now, one of the things, of course, that is difficult as well is to understand what the future will look like. So we have to be able to make predictions into the future. And in order to do that, we need to develop and build some models. Now, those models, and Ben referred to one that I've been working on for some time, are often very complex and are very difficult really to understand what's going on and to explain. But we don't need to rely upon those models to actually understand what's happening in the orbital environment. We can actually look to natural populations here on the Earth because the way in which those natural populations grow is very similar to the way in which the space debris population grows as well. So there are very simple models that we can use, exponential, logistic models that we can use that describe how natural populations evolve. And we can use exactly the same kind of models to describe how the space debris population grows. But I can't really continue with this particular metaphor using things like penguins and so on, natural populations. We have to try and consider a slightly different type of population so we can think about, if you like, our behaviors and rules that we might need to control the population. So there's a very different type of pseudo-natural population, again, that was born out of our imagination, which has a set of rules associated with it. So if you've seen this movie, you might recall the rules that exist to prevent the growth of this particular population. We do not want to expose these creatures to sunlight. We do not want to get them wet. And above all else, we don't want to feed them after midnight. Those are a set of rules that constrain the growth of this particular population. And this particular population, if we don't follow one of those particular rules, we end up with quite substantial problems. So this is a really good metaphor for the space debris population growth. We talk about exponential growth in the number of objects in orbit, but we have a set of rules that we can follow that will constrain that growth. There are questions about whether those rules are sufficient and whether we need to think about some alternatives, but they do exist. And it's really important that we continue to observe them, implement them where we can. If we are to do that, one of the things that we find is that we can actually constrain the growth in such a way that we don't see this continuing exponential growth. And what that means is, if we kind of reverse that, is that if we perhaps exceed a certain population level, then the rules stop working and we see the exponential growth. We're defining, if you like, a carrying capacity. So illustrated here using the bucket and the water, there's only a certain amount of water that I can fit into this bucket. Any more and it starts to overflow. And the same is true in the orbital environment. But as soon as we start thinking about the orbital capacity that might exist, how many spacecraft can we actually put into the orbital environments around the Earth, we start to run into some additional problems, because we're kind of talking about lots of companies, governments, and so on want to use space. So it's a bit like inviting 30 friends to your dinner party and then offering them 20 cookies. Who gets the last cookie? That's kind of what we're talking about when we talk about orbital capacity. Who gets to use the remaining capacity in low Earth orbit, and how do we decide? So that's a really challenging social problem. And I think what I wanted to do with that is to illustrate it's not just a technical problem that we have to solve, it's a social problem as well. And it's even perhaps worse than that, in the sense that if we look at the orbital environment, things that happen at relatively high altitudes are going to affect satellites and so on at lower altitudes. We saw that this week. The International Space Station performed a collision avoidance maneuver to avoid a fragment from a satellite that was destroyed back in 2007 at a much higher altitude. In fact, at an altitude that's more than twice the height of where the International Space Station is. So we see activities somewhere else in the orbital environment will affect our activities elsewhere. And it's not even the end of it there, because what we also have found is that our activities down on the Earth, emissions of greenhouse gases, causes the atmosphere to change. And we're seeing that not just at the lower parts of the atmosphere, we're seeing it high up as well, where the satellites are orbiting. So our activities down on the Earth are affecting our use of space. And we can also see that our activities in space also potentially harm our activities on the Earth, such as astronomy. And this is a really important point that is being discussed at very high levels at the moment, how we can still use space, but without harming the science and our understanding that we get from activities such as astronomy. So there's a lot that we've got to think about. But what I'd urge you to do is, whenever you think about the environment down here that we all occupy, that we're all connected to, we have to also consider the environment that the satellites orbiting. It's actually one environment. They are connected through our activities and through the harms that we do in both regions. And it's really important that we remember that when we try and tackle either of these kind of problems. So that's where I want to leave you. I'm using this particular image as a way to think about what the potential solutions might be, and as a way to start the conversation. So thanks very much for listening.
Wow, well, thank you so much, Dr. Lewis, for that intro. I want to say I am blown away that you were able to announce live on Twitter of what you just did. For those of you who may have missed this, he tweeted yesterday, for this event, I'm going to try to provide a different way for you to look at the space debris problem, featuring Tuvalu, a cookie, a witch, and some penguins. I was excited, maybe a little bit skeptical, but it just happened. And so that's really awesome to see. So I'll just take moderator's prerogative to ask in the first framing question before we go to the rest of our expert panel. So just to step back a little bit, scientists' realization of the effects of space debris dawned in the mid-20th century about the same time that climate change threats were better identified and better modeled. Of course, very famously, NASA astrophysicist Donald J. Kessler published a seminal paper in June 1978 in the American Geophysical Union's journal, warning that, quote, satellite collisions would provide orbiting fragments, each of which would increase the probability of further collisions, leading to the growth of a belt of debris around the Earth, adding that, quote, under certain conditions, the belt could begin to form within this century and could be a significant problem during the next century, meaning the century we are currently in. This process became known as the Kessler Syndrome, and to me, it really feels like it has distinct conceptual parallels to the climate change tipping points temperatures for Earth's atmospheric system. And this has been a cautionary regime that has helped drive thinking on space debris mitigation regulations in the decade since. So my first question to you, Dr. Lewis, is how close are we to a Kessler Syndrome tipping point, and how do we avoid such a disastrous scenario?
Thanks for the question, Ben. It's a really good one. And we have to kind of unwind it and unpick it a little bit, because there are similarities with climate change, but the similarities aren't quite what we perhaps might think. The space debris population and the processes that are involved in producing more space debris are actually quite simple. The feedbacks and that encourage the growth of population are basically, there's one, which is collision activity. That's what the paper by Don Kessler and Bert Corpallet investigated. So when you factor that into your understanding, it means that there aren't really any tipping points as such, not in the same way that you'd see for the climate system. What you actually see is this evolution, this smooth evolution in terms of the population, which is why I refer to the natural population and exponential growth. So what you can see with the evolution is that it can look quite benign, this kind of fairly flat growth, and then what you start to see is this upturn and that you would get from a characteristic exponential curve. And my understanding from the modeling, from looking at this, is that we're on that kind of flat part of the curve. It's growing slowly. We started to use space a bit more. And then some point in our future, what we're going to see is that curve starts to get a lot steeper. And there won't be sudden warning. There won't be anything that we can point to. And that was the thing that did it. It's actually all of our activities in space that contribute to that process. So I think the actual answer is that we're probably already on that slope that Don Kessler was talking about. And we have to take some action if we don't want the future that he envisaged to take place, whether it's this century, whether it's the next century. We have to take action.
I'm going to turn next to Professor Britt Lundgren to ask a question here.
Sure, thanks, Ben. Dr. Lewis, I really appreciate you bringing up the complication from a social perspective of solving these problems. I'm an astronomer, and so I am well attuned to the problem of satellite trails in ground-based imagery, and also the increasing danger to our best and most expensive space-based observatories like the Hubble Space Telescope, as the movie Gravity showed, right? But at the same time, my own parents live in a rural part of Colorado and have signed up for Starlink for coverage of broadband in their area. So I understand how complicated this can be. And there's great opportunity for many people who otherwise aren't connected to the kind of opportunities that satellite communications bring to their communities. Though at the same time, it's not clear that large satellite constellations are yet accessible financially to those same populations. So I'll say that. But I think another thing that gets less attention, but has recently been published by a group of astronomers, is the actual problem of light pollution from not only the existing functional satellites and those that have been retired, but also even these very small pieces of space junk that you mentioned are found in the millions in this part of low Earth orbit. So the best estimates to date that were published in March in a recent journal said that we're already at a 10% increase in brightness relative to the natural dark sky. And the problem with this is, unlike city light pollution, which you can drive away from, this kind of light pollution you can't escape, even in some of the darkest regions on the Earth. So this is something that I am becoming increasingly concerned about as we see more and more of these applications for more and bigger satellite constellations. And I was wondering if you have any thoughts about that as well.
Many thanks. Yeah, you're right. It's a difficult problem to address. I think what we see, especially on social media, that it's actually quite a polarizing problem, isn't it? In the sense that many people are for, many people are against, and it's very rare to find perhaps somebody in your situation where you can see both sides of that particular problem. But I think that's the reality at the moment. That the way in which we manufacture and we operate spacecraft, it leaves behind some legacy. Ideally, nothing, leaving no trace. But we have to recognise that in reality, our use of space causes some harm to that environment. And so no matter what the service is and the value of that service, there is going to be an associated harm. And then the question is that harm worth the benefit? And I'm not really the person to answer that. That's probably something that needs to be discussed, absolutely. But as an engineer, that's something I struggle with, to find where that balance point might be. But it's something that I think we have to acknowledge at the moment. So unless we change how we design and operate in the satellites, then that problem is always going to persist. And so you mentioned, the dark sky and the light pollution that exists thanks to not just new and upcoming space systems, but also the legacy of 60 plus years and so on. That's a really hard one to deal with. And I think what's happening as a result of the ongoing discussions about the impact of new space systems, on astronomy and on the night sky, we're starting to learn that actually the potential consequences of space debris go far beyond the harms to the satellites, that there is actually a much broader environmental problem that needs to be addressed. That's only really just starting to occur to the community that I work in. So we have to kind of expand what we do when we start to think about the space debris problem. We have to expand understanding of what the potential harms might be. So that's early days. There's still a lot of work to do, and obviously a lot of discussion to be had. But actually, that's something that I think, in spite of the difficulties and the challenges, obviously, that your community are facing, that's something that is starting to emerge, that those conversations are happening. So whilst there's no easy solution, and there's certainly no solution that we can point to immediately, I think it is a positive step forwards that we are discussing it, and that there hopefully will be solutions that exist.
Great. And sticking with this topic a little bit, I'd like to go over to Professor Newberg, our other astrophysics professor on this panel, before we go to the diplomacy and policy issues. So over to you, Professor Newberg.
Yeah, thanks. So sort of amplifying that same point, I do more radio astronomy. So so satellites, things like Starlink for us, we don't see them visibly. Like, there's reflected sunlight and stuff, and that makes them very visible with these expensive telescopes that Britt uses. Our concern is things like the radio frequencies that these satellites like Starlink use as their communications frequencies are bright for us. We would like to use those and for science, and they're beaming enormous quantities of power from each one of those, literally over 1,000 satellites. They're beaming them directly into our telescopes, more or less. I have to admit, my sense of this felt like it was kind of unregulated, like Starlink just started existing, and it felt like there were not a lot of questions. There wasn't any, it didn't feel like there was a lot of input from the scientific community, or wasn't requested from the scientific community about whether these bands are used. In radio astronomy, every tiny little frequency chunk is sold off to telecoms, for billions of dollars, sold off to communications companies. And it felt like space was just this like wild west of you can do anything. I'm probably wrong about that, but maybe you could speak a little bit to what sorts of regulations, if any, people are putting in place for these satellites. The astronomy community has started to get much more serious about advocating for clearer skies and for our telescope bands. But I was just wondering if you knew much about the sort of the regulatory environment for these sorts of satellites.
And I do want to just share for a visual for the audience before taking over to Dr. Lewis to answer that great question. What are we talking about when we're talking about Starlink? All of these paths, if you can see the screen that I'm sharing, are Starlink orbital paths on the StarTrek.org data set. That is pretty astounding for the amount of coverage that already is there with just the thousands of Starlink satellites, and obviously they're ramping up to tens of thousands. So I will stop sharing and take it over to Dr. Lewis.
Thanks, Ben. Yeah, actually, it's really good to be able to see that because, as I said, we have to use our imaginations for this particular problem. So the visualization tools. Again, it's really important to stress that the images I've shown, the images that Ben's put up, they're illustrations of the problem. The debris obviously aren't that size, so we have to absolutely recall that. But to come to your question. So I'm not involved in the regulation that surrounds spectrum and frequency allocation. My understanding is, I think you actually referred to it, that there are reserved parts of the spectrum, and then other parts of the spectrum which are essentially sold off and so on. There's potential, obviously, for spillover and so on. Now, the mission, if we take Starlink as an example, the mission objective is to essentially send up lots of radio broadcasting satellites. So it's very different from the situation with the reflectivity of the satellites and so on, which is, if you like, you can consider to be a harmful byproduct of the activity, but something that you can try and mitigate. Whereas when you've got a satellite that is broadcasting and that's its function, that's very difficult to try and mitigate. Hence the division of the spectrum, or you hope the division of the spectrum starts to take into account that kind of thing. But clearly, it's the best case scenario is that we're encroaching upon those reserve bands, and the worst case scenario, that we're actually starting to blanket those with the broadcast from space. And obviously, I understand that gives you huge pause for concern. But actually, with respect to both of your questions, and I say I understand absolutely the concern, it's not a new problem. Back in the 1990s, there were discussions on the impact of satellites on the night sky and on radio astronomy. And there were substantial efforts taken then to try and address the problem, with calls to the international community. UNESCO organized conferences and workshops to talk about this. And I think what's perhaps troubling for me is that here we are 30 years later, and we're still experiencing the same issues, and perhaps we haven't been able to take advantage of that last 30 years to try and solve these issues. The only thing I can say is that I'm pleased that the conversations are happening now. But as I say, if we're to avoid having another 30 years before we solve this, then actually we have to make some progress. And I think that means compromises, that means some difficult decisions, and it also means that regulations may certainly be needed. So I'm afraid that I don't think there's an easy answer actually to either of your questions just yet. My hope is that something starts to emerge that we can start to all agree on.
Thanks. And I think that through this discussion already, we can see this is a truly global problem. And our program really thinks that world leaders need to be part of any science and technology oriented policy solutions, especially in terms of practitioners of science diplomacy, which this is certainly right in the wheelhouse of. Ambassador Pearson, you've talked a lot about anticipatory diplomacy. And I really want to just kick it over to you to for any comments and questions you have on the need for anticipatory diplomacy to clear the way for base debris clearing technologies, for regulations, international norms, and communications channels.
Thank you very much, Ben, and thank you to our audience for being part of this conversation today. I think it's a part of an essential step to learning how to deal with these issues. So I was especially interested in hearing Dr. Lundgren and Dr. Newberg explain their perspectives on these issues. I've maybe spent 40 years in diplomacy of one form or another. And of course, to a diplomat, like the guy who has the hammer and everything looks like a nail, to a diplomat, everything looks like a problem to be solved through negotiation and human relations and human understanding. And in my opinion, that applies here as well. I'm drawing another and underlining a metaphor that Dr. Lewis made between climate change issues and space. And that is that now we see large segments of the world population, especially young people, the public, directly and forcefully and aggressively involved. And I think that in trying to deal with normal problems, it is the impact on the average person's life that begins to awaken the process of solving the problem. So one of the things I might add to the discussion is it's one thing for the scientific community and the government leaders to be talking with each other. That was true for climate control for maybe 30 years. It's more important at this point in time to begin the process of involving the general public and the effect on their lives, whether it's health or technology or access to things they expect, that is important. In many, many studies, humans choose to avoid danger rather than to take a risk or achieve a benefit. And so one of the things you can do in diplomacy first, and I think this has been alluded to, is figure out what you're going to stop doing that's doing harm to everyone. So I think about that. Diplomacy is a long game. It's now taken 50 years to create a crisis about climate control. It took over 10 years to get the first nuclear disarmament treaties signed. It took 10 years at least to get the Antarctic Treaty signed and the Outer Space Treaty signed. So part of the work of diplomacy is to start in the center with shared interest and no blame, and begin to work outward on points that are of benefit to all, although they are not the ultimate wish of anyone. And that's a hard process. So that really is a comment about the issue. It's one thing to talk about what ought to be done, but a quite different thing to say, this we will do, this we will propose to do, because that engages governments, politics, interest, the profit motive, the ethical and moral considerations, the whole kit and caboodle. And so that's how we need to start. And thank you very much for the opportunity to offer these thoughts into our discussion today.
Thanks, Ambassador. If I can just pick up on what you said, and I think to come back to Dr. Lundgren and Dr. Newberg as well. One of the things that you talked about, of course, is it's a long game, long process, and we've heard about the challenges in the astronomy field, space debris, but we've also seen the benefits that come from Starlink as well as an example. And then the question is really, how do we manage to get people to agree on a way forwards when actually all of the sides are almost so opposed? You know, that I refer to it, and certainly on social media, that it's a kind of a polarizing problem. So do you feel as though the negotiation, the diplomacy role still works?
Well, I do. I think looking at it another way, there are two philosophies at play on the issues of space that were in play on the issues of climate change. One is the Crywolf Syndrome. For many years, people talked about the damage being done to the climate, but no one responded to the alarm sufficiently. And that's because it didn't happen immediately when Crywolf first was the call for action. And we know from studies that crying wolf gradually diminishes the sensitivity of the audience to a solution. And the other syndrome is the Kessler Syndrome, which you very well described, which is well-meaning but interpreted publicly and popularly as a kind of, you'll never solve this problem because it'll just get worse faster than you can make a difference. So that's the despair solution. And so diplomacy has to pick something to begin with. And when I said that no is a good opportunity to begin with, think about the treaty to end nuclear tests in the atmosphere. That began with a no. Think about the Antarctic regime and the agreement not to commercially exploit or grant, I will call it national sovereignty to land in Antarctica. That was a no. There are no's also in the laws of the sea. So those are the kinds of things that can be thought to start with. So I would just suggest that in looking at space, there are some things that we could begin with that could help alleviate the problem. And let's start with something that proves the theorem, if I may say so, rather than dwell too much on how terrible the crisis is, because it will be terrible if we don't do something about it. But it's not so terrible today that the average person sitting in their living room thinks about space as opposed to climate change. And so part of the work, which I mentioned earlier, is getting the average person around the world to see something. I believe that in a previous occasion, you mentioned loss of GPS as an example, but something that impacts daily life and makes people come to an aha moment where they believe that they need to be engaged.
Thank you. I mean, I'd love to hear the thoughts of Dr. Lundgren and Dr. Newberg, actually, because something that I actually believe in is there is something that connects all of humanity to space, and that's the night sky. You know, in the sense that what we would hope for all of humanity is that they can experience perhaps the same wonders that astronomers have seen, even from cities. That used to be the case. You know, the Milky Way could be seen from even some of our major cities around the world. So I think, you know, to pick up on your point about, you know, finding something that we can all agree on, and also finding something that actually connects us as human beings to this particular problem. I think the night sky actually provides us with that opportunity.
Professor Lundgren?
Yeah, so I would just add, you know, just like Ambassador Pearson was saying, this is a kind of slow boil, right? Just like the climate crisis has come upon us in a reasonably slow way on the span of a human lifetime. I think the light pollution aspect of this crisis has also arisen slowly enough that people haven't noticed. Whereas now, you know, I'm teaching in a reasonably rural part of the southeastern United States. And when I ask my students in a class of 40 how many have seen the Milky Way, I get one hand raised in their entire lifetime, right? So it's not uncommon to not be able to find dark skies. And I think that it's, you know, it's something that if policies are being driven by people who work in urban populations, they may not even during their lifetime realize what they've missed. Whereas, you know, the problem with the space-based reflectivity of all of these satellites and other pieces of junk, you know, that's now to the point where it's starting to affect really remote indigenous people who actually rely on the sky to maintain their cultural heritage, right? And they have less of a voice, I think, in driving the kinds of policies that will eventually, hopefully, regulate this kind of, you know, expansion of technology in low Earth orbit. So it's, yeah, it's something that I worry most people aren't even really fully aware of because they, in their lifetime, haven't actually seen a proper dark sky.
Professor Newberg, you want to add to that?
Yeah, I guess I'll just comment to say, in science, a lot of times also we find new things by measuring in new frequency bands. And so we also may lose out. I know it sounds like a fluffy concept, but, you know, we may lose out on science because we never got to measure it from the ground, simply because we, you know, in the experiment I'm working on right now in the radio, our frequency of interest just basically got sold to a telecom industry. And so the experiment can exist right now, and in about 5 years, it won't be able to anymore. And so we managed to get in at the nick of time to be able to make the measurements we're making. But you know, that will happen over and over and over again. And so you know, there's a protection perhaps of the future of science as well that we should at least keep in mind. And I know that doesn't go to the ambassador's point that something like that directly impacts anyone's life. But you know, science for future generations is also you know, something that that certainly I think about.
And I would just add that something that the kind of satellite trails that we now are dealing with increasingly in ground-based imaging, can actually impede our ability to detect life-threatening impacts, right, from near-Earth asteroids. So I've mentioned this in a previous discussion with other panelists here, but that's also something, it's not something I personally work on, but I'm glad other people do. And I think that we're probably not doing a good enough job of kind of expressing that concern as well as scientists.
Okay,
it's interesting. Sorry, Ben. No, I was just going to say it's interesting because often what happens is when you raise these concerns is that the popular opinion is, of course, is that we can just stack the images and therefore remove the trails and we haven't lost anything. But that you've just given a perfect example of something where you can't do that. And transient events and so on, which are really important. There isn't an easy solution that I think many people believe that there is. So yeah, thanks for raising that.
And I'll just say to Professor Newberg's point, on a panel with I think all space enthusiasts and at least 3 astronomers specifically, I don't think anyone thinks those concerns are fluffy or something to be dismissed. So I do want to turn to the audience questions now. We have one from George Sibley, who says, while the top priority needs to be reducing rate of addition to this to space debris, is there a plan for seeking a way to begin removing some of that debris? And I will add to that by saying that this clearing of the mess is at once a daunting and enticing challenge for both government and commercial technologists. And we see 21st century solutions being promoted. The potential to use lasers to ablate the side of space debris to get it to deorbit. We also see on-orbit mechanical systems that have decidedly not so 21st century technologies involved, including a British University's 2018 demonstration mission that used a harpoon and a net. So I want to have that question and add to that a quote from Australian space debris expert Alice Gorman, who explained just recently in Scientific American that any successful technology that can be used to remove an existing piece of debris can also be used as an anti-satellite weapon, which is a really good point for a national security and diplomatic consideration that we're discussing today as well. So how do we differentiate the two? What are the possible solutions, and how do we regulate this going forward?
Yeah, I mean, it's such a complex problem, and at the heart of it is transparency and behavioural norms. So if we can be transparent in terms of our operations in space, and if other people can understand what we're doing and why, then the dual purpose nature and the worries associated with that Dr. Gorman mentioned, they can be somewhat dealt with, and that's why you're starting to see initiatives being brought to the United Nations about transparency, behavioural norms, and so on, because there is every danger that we misinterpret some actions in orbit. And that's perhaps to be expected, given obviously space is providing us with this opportunity for national security, for surveillance and so on. There are bound to be times where government entities are going to essentially fall foul of one another in the orbital environment. But if we can understand what that's about, then we can avert any escalation of the situation. So those efforts that are happening at the United Nations and the initiatives that are brought there are so important. But they are essentially working towards a problem, if you like, of our own making. And I say that it's a bit strange to say that, because space debris is a problem of our own making. It's a purely technological problem, and we've caused it. But it's there because some government agencies are going to inspect other satellites, and they are conducting missions that are the objectives are uncertain, shall we say. So the transparency and the norms are important, but they're not a solution to space debris. They're not a solution to space sustainability. and they're not a solution to the potential harms that are occurring to science and astronomy. So the solutions that do exist are, we're starting to see those now. So companies like Astroscale, ClearSpace, and in the US, we're seeing in-orbit servicing kind of missions that are taking place. These are the first steps towards removing the legacy of the last 60 years and to improving the environment. Human beings are really smart. We're creative, great at solving problems. So you may wonder why it's taken us this long to get to the point where we're actually just conducting demonstration missions on really small targets that are well prepared and so on. And a lot of that is about effort and concentration on other problems. Remediation, which is what we're talking about, wasn't seen to be the most important thing to focus on. What many governments felt was more important was to focus on complying with space debris mitigation rules, which are all about preventing the new debris from being created and getting operators and so on to comply with those. Space debris remediation, the active removal of debris, was kind of left behind in that, and now we're only seeing that. But the other factor is cost. It's hugely expensive. So there has to be a financial incentive for people to do this, and that's perhaps only just starting to emerge. Ironically, perhaps as a result of lots of mega constellations that are being proposed and are flying. As a result of that, we start to recognise that on a commercial basis, those operators need their orbital shells to be clear and pristine so they can continue operation safely. So talking to companies about removing their failed spacecraft or any bits of junk that exist in their vicinity is good for their business. So there's a creation of a good business case for debris removal. So, in many senses, we should be decades further along in dealing with this problem, but there are very valid reasons why we're not. And some of it is to do with the transparency and the behavioural norms that I talked about. Some of it is technology. Some of it is business. Some of it is politics.
Thanks. And I want to bring Ambassador Pearson in on this point because in your diplomatic experience, certainly attributing intent is often a major challenge in both military and foreign policy contingencies here on Earth, and the opportunities for miscalculations, as Dr. Lewis points out, multiply when the action is taking place off planet. We have a few questions that have come in on the potential for conflict in space in mitigating the potential for a future, a war domain becoming prevalent in space. So, Ambassador Pearson, what lessons can we take for those points of transparency that Dr. Lewis was talking about, and assigning intent and understanding intent of other actors, from a geopolitical standpoint for activities in space?
Well, that's an excellent question, and it has a long history. So humans compete, and they compete for individual advantage, for group advantage with the group they identify with, and they compete to diminish the influence and strength of groups that oppose them. That is a reality that runs through all of human history, and it's not going to change. So diplomacy has to start with that reality. There is a global national security race underway, and there is no way to deny that or to obfuscate it. There are on the high seas rules of engagement about ships approaching each other. We've had examples of probe satellites from one country approaching the proximity of a reconnaissance satellite as if it were testing how close it could get if it needed to destroy that satellite. Those are the kinds of behaviors that China, Russia, the US, the European Union, Japan ought to be able to negotiate among themselves to begin with. Another idea, and maybe it's because I'm not a scientist that I have the temerity to suggest it, is that those countries that launch into space agree that the launch booster vehicles will return to the atmosphere. This is a technology that we have and that others could have. I don't think the Chinese do that at the moment, but that would be another example of no, where they safely put the booster back into the atmosphere to burn up in a safe trajectory. Those are examples of ways that you can get started to deal with some of these issues that are national security in the sense that Dr. Lewis mentioned, and that is removing the clutter makes the communication satellite and the benefits to humankind more likely to continue to exist and to grow. So I offer those two examples, but there is no way to avoid national competition in space, including in Earth orbit and on celestial bodies. So we have to develop the rules to do that. And I know the UN has done a lot of good work thinking about this, but it requires the agreement of the 5 major space entities to begin to solve that. And we could start coming up with some of those ideas.
Thank you, Ambassador Pearson. Dr. Lewis, I want to ask you a question that came in from one of our audience members that I think you'll have a good handle on, because it sounds like you may be on some of these organizations yourself. Does the US or any nation have an EPA, Environmental Protection Agency, type organization for space debris that requires new space launches and satellites have an environmental impact study and adding that to its impact on the space environment that has any public participation or oversight? So what can we see in terms of international organizations or national organizations that are really looking at that environmental impact assessment, EIA process, but for space debris?
Yeah, so certainly there are mechanisms for this, but it's really important, I think, to understand the history. So, thanks to negotiation and efforts back in the 1960s, we have a treaty that relates to outer space, and in that treaty, there's talk of preventing the harmful contamination of outer space. And whilst the wording was perhaps ambiguous somewhat, what is contamination? Many states, interpret that to include space debris. So therefore, there's an incentive for those states to, especially being signatories to the treaty, to actually prevent the harmful contamination, to prevent the generation of space debris. So those nations, in order to comply with that and to meet their obligations, will create, almost certainly they'll create a licensing regime, some kind of regulation that essentially provides that initial review of a space system before it gets launched to determine whether or not that system is going to potentially contaminate the environment and expose that state to a liability claim. So that process does exist. It's not standardized across the world. So that, you can kind of go shopping for the best deal, as it were, depending on what your space system looks like. So there is some concern there about that particular aspect, but it is there. So and part of that would be typically some kind of environmental assessment, a space environment assessment, it's important to say, potentially looking at the collision risks, looking at the long-term population change as a result of your new space system flying. Now, the difficulty that emerges from this is, as I say, is where do those rules come from? Because the Outer Space Treaty is not, it doesn't prescribe what those rules should look like. So then we have other organizations, and in particular, the one I'll mention is the Interagency Space Debris Coordination Committee, the IADC. This is an organization, it's an intergovernmental organization. So you've got 13 major space agencies that all talk to each other. They meet on a regular basis to discuss the technical issues And they came up with a set of guidelines, space debris mitigation guidelines, which were then adopted by the United Nations. And you find that these variants of these exist within the national regulatory schemes that exist. So there is this kind of international effort to provide some guidance to identify what good behaviors look like, and then the national regulators pick these up. Now, what's emerging as a problem, I think, for some of these space systems is that the typical environmental assessment you might want to make is not being made. So there's obviously a case involving a particular operator, which was brought to court, I think, in the US. And the issue is whether an environmental assessment should be made. And the argument has been that the regulator has offered is that space is not a human environment. So therefore, no environmental assessment is required. What I try to do in my talk is to demonstrate that actually there is only one environment, and actually you can't easily separate the space environment from the terrestrial environment. There are crossovers that happen all the time. So I think it's a real problem that we've got. But the good news is there are some types of environmental assessment that are being made. So hopefully that answers the question that's come in to at least to a certain extent.
I think so. That was really great. Well, we are running out of time, and I want to spend the last 10 minutes or so giving everyone a last word, and then we'll come to you, Dr. Lewis, to wrap up and give your prognosis for where things go next. But let's start with Professor Lundgren.
All right. Well, I can keep it short. I think I've said most of my key points, but I appreciate, as someone who always wanted to be an astronaut, I appreciate all of these efforts and building up low Earth orbit and beyond. But I guess my final kind of plea would be to think about when people say that, I should be specific, people such as Elon Musk have made claims that all telescopes will have to move to space, right? Because the satellite problem is just it's just here to stay, right? But then of course, if we're not careful about the carrying capacity of low Earth orbit, even space is not safe for our instruments and our progression of knowledge. So I think there are lots of stakeholders, not just in the astronomy community, but stargazers around the world have this cultural heritage that I have an interest in helping to preserve. And so I'm really grateful that this conversation has happened today. And I hope we can make some progress.
Thanks, Britt. Ambassador Pearson.
I really liked Dr. Newberg's reference to the Wild West. It is the Wild West. And in human history, unrestrained competition has always led to war. And so I would just ask that all of us involved, including our audience, remember that helping spread these concerns to the general public so they understand what is at stake. The work that Dr. Lewis has mentioned about norms of behavior, but this is really a long process, and we are at the very beginnings of it. But I would try very hard to pick something that's visible with a beneficial impact. To me, it was getting the boosters out of orbit that would enhance the integrity and the national security of Earth orbit, and could be a basis for starting broader elements of agreement. So that's my offer, and I really appreciate being on the panel today and learned a great deal. Thank you so much.
Thanks, Ambassador Pearson. Professor Newberg?
Yeah, thanks so much for inviting me on the panel. I've learned a ton. Yeah, my comment, I guess, is just, the beginning of sending stuff into space started with science. Some of us are maybe some of the first people, realizing the impact of the space debris on our telescopes. And, I think for people to get invested in the solutions, it needs to touch their daily lives, as many people have said, through things like maybe your GPS will no longer work and your phone will be useless and everyone would cry. But there are also, large issues confronting us as scientists for how we can be part of the conversation going forward to protect some of the things we care most about.
Thanks, Professor Newberg. And as a fellow astronomer, I can't agree more. I'll point out to the audience that the Hubble Space Telescope didn't just come up in the context of the film Gravity. Damage from space debris impacts were observed firsthand by astronauts on solar panels of the Hubble Space Telescope back in the 1990s, which was one of the first real wake-up calls in real time and in person in space of this issue. I'll just say that much like climate policy developments, no single nation can solve this problem on its own. We have a path forward that is complex, but it's clear. As we continue as humanity to extend and expand our space footprint, we need cooperation like we see here on today's panel between scientists, between diplomats, between regulatory experts, between technical experts, and have that multidisciplinary study and have that come together around the globe to move to the development of space debris mitigation norms, communications channels, and technical solutions, and moving that to the center of the active foreign policy agenda. I think that is really going to be necessary as we continue to see headlines of space debris and anti-satellite testing and things like this becoming very central national security issues. Over the next decade, I think we're going to see that increasing to the level that the general foreign policy community, I think, will have to include this in its national security strategies. So with that thought, I'll give our last word for the next 5 minutes to Professor Lewis, who has just done a tremendous job to talk about all of these really fundamental issues today.
Many thanks. Again, really appreciate the invitation and the opportunity to have such an engaging conversation and to learn, especially to learn different perspectives, I think, which is always important and valuable. I started with a series of movie references, so I'm going to end with a movie reference as well. And a reminder that space is wonderful. Space presents huge opportunities for many things to benefit humanity, and we mustn't forget that. And what you've probably heard today, there might not have been enough of that in there. We've heard about the problems and the difficulties and so on that we need to address. So I'll end with this reference, and I've ended some talks with this before. There's a scene in the movie Terminator 2. The character Sarah Connor is carving something into a bench, and what she's carving are the words "no fate." And the kind of full line is that there is no fate but what we make for ourselves. And what that means is, you've heard about some dire predictions. You probably know about the Kessler Syndrome. And the conversation today has been perhaps quite pessimistic. But there's every opportunity to be optimistic here. There is no fate but what we make. And it's not necessarily going to be my generation that solves this problem. It's probably going to be the generation that follows, the people who are listening here today. So I'd encourage you to use your imaginations, use your ingenuity, use those very human skills and qualities that you possess. Don't just focus them on the environmental issues that you see right in front of you. There are other issues that deserve attention and your effort. And I'd encourage you to work hard towards helping us to solve those, so that we can boldly go and we can enjoy all those benefits that space offers.
Well, thanks so much, Professor Lewis. Really, really inspiring comments, and it's given us a lot to think about on a Friday here. So thank you so much for your time. Thank you also to Professor Britt Lundgren from UNC Asheville, Professor Laura Newberg from Yale University, Ambassador Robert Pearson of the Rethinking Diplomacy program at Duke University. And again, I'm Benjamin Schmitt from the Harvard-Smithsonian Center for Astrophysics, and also a Rethinking Diplomacy fellow here at Duke. Please stay tuned. We will continue this series of space diplomacy events. As Professor Lewis hinted to, yes, we need to look to each other and to other nations around the world in our ability to address global challenges. But we should also, as diplomats, as scientists, as humans, keep looking up. Thanks so much.